In Chapter 3, we're going to look at derivative rules for a bunch of kinds of functions. And we're going to start with looking at powers and polynomials. So in section 3.1, we're going to learn the power rule and be able to apply that power rule for differentiation. And we're going to compute the derivatives of sums and differences, allowing us to compute derivatives of polynomials in general. The power rule states that the derivative of x to any power is going to be the power times x to the power minus 1. So we have x to any power. What we're going to do is we're going to think about taking the power out in front of the x and then decreasing the exponent by 1. And this works for any real number p. The only one that's kind of weird is p equals 0, but note that it still works here. So let's do the derivative of x to the 0 is the same thing as the derivative of 1, as that's what x to the 0 is going to be. And note that the derivative of 1 is 0, which is also the same thing as 0 times x to the 0 minus 1, which is itself just 0. So admittedly, that one's a little bit weird. But other than that, this holds true for every real number p. So let's do some quick examples to see how this is going to work. First, let's think about the derivative of 5x to the 7th. Remember that we can take constants out in front. We're going to learn we can take constants out in front in a little bit. This is going to be 5 times the derivative of x to the 7th. And x to the 7th will be 7x to the 6th. The derivative of x to the 7th is 7x to the 6th, which means we're going to have 35x to the 6th here. We'll see on the next page or two how we are able to take the constant out in front. All right, the next example does not look like x to a power, but we can use some algebra here to rewrite it as x to the power. So first of all, note that this is the same thing as the derivative of 1 over x to the 1/2 power, as that's what a square root is telling us. And then note that we can write 1 over x to the 1/2 as x to the negative 1/2. So now this looks like x to some power, and the derivative will be, bring the power down out in front, negative 1/2, x, and then we're going to have negative 1/2 minus 1 exponent, which we can write as negative 1/2 x to the negative 3/2 function, or power. And there is our derivative. So this is a rule that we're going to use all the time. It's going to be our most common derivative rule, the power rule. So let's see why this is true for p being a positive integer. And note that the proof for this past that is going to be a little bit more challenging. So we're just going to stick to this one to kind of show some reason why it's true. Note that for all or almost all derivative rules that are going to be brought to our attention, we are going to go through and see why they are true. It's not enough just to assume that it's true. We're going to try to show why. That being said, you are not going to be responsible for a proof like this. Right? This requires some kind of algebra that's a little bit much to assume that you know how to do something like this, but it's good to see done. So what we should be able to do is to start with our function, our derivative, and then rewrite that as a limit, as that's the limit definition of the derivative. Our function is x to the p. We replace x plus h with the x, and then subtract the function. And then note that we are using the binomial theorem to rewrite x plus h to the p as x to the p plus px to the p minus 1 h plus on and on h to the n. And I didn't write all the terms down for one reason, because it's a lot to write down, but also because the constants out in front change past those first two. So for example, let's look at x plus h quantity cubed. We could write this as x cubed plus 3x squared h plus 3xh squared plus h cubed. And what's going to be true of all these terms is they have at least an h squared term or more past that. So everything in here is going to be at least h squared. And the reason we're not going to care about that is because it's all going to go away with the limit h approaches 0. When we do this binomial theorem, we expand it out, and we know that we can cancel out an x to the p here and an x to the p there. And we kind of said this is going to happen. We should get rid of all the h's in our limit, or everything without an h should go away in our limit. What we're left with is a bunch of stuff with h, noting that everything past this first term has at least h squared. We're then able to cancel out an h out of every single term, and we are left with px to the p minus 1 plus a bunch of stuff now with at least h. So when I plug in 0 for h to do the limit, all of these terms are just going to go to 0, and I'm left with px to the p minus 1. So once again, you are not going to be responsible for replicating this proof, but you should have some kind of idea as how we get from one step to the other. So then as we try to find the derivative of polynomials, we need two rules that are going to look very similar to rules we've seen with limits. And the reason they're true is because a derivative is a limit. So the first one is the derivative of a constant times a function. That's what we did in the example on the previous page with 5x to the 7th. So if you want to take the derivative of a constant times a function, you're going to bring the constant out in front of the derivative and then take care of the function. So for example, the derivative of 5x to the 7th, we wrote as 5 times the derivative of x to the 7th. And we can see this is true based on the limit definition of the derivative. So if I have the derivative of c times f of x, when I plug it into the limit definition, that's going to be c f of x plus h minus c f of x, and I can factor out a c out of both terms and bring that out in front. Then we have a rule that we can bring a constant out in front of a limit, and therefore we're left with c times the limit definition of the derivative. That whole thing is f prime of x. And there is our answer. So a lot of the same reasons we can do things with limits, we can do with derivatives. I can bring constants out in front of limits. I can bring constants out in front of derivatives. When I take the derivative of a function plus another function or minus another function, I can take the derivative of each separately. Let's see this is true with just a plus instead of the plus minus. It's a little bit easier as we get our signs kind of mixed up without that. The derivative of f plus g, when we plug this into the limit definition, I have the x plus h part, that's f of x plus h plus g of x plus h, that's one big function, minus the f of x plus g of x, and then I'm just going to rearrange the terms. I'm going to put the f's together, I'm going to put the g's together, and that's going to be an f of x plus h minus f of x. Note that I need to distribute this negative to both terms. And a g of x plus h minus g of x. And then we use the rule for limits that we can break a limit of things added together into separate limits, and I'm left with the limit definition of the derivative for f plus the limit definition of the derivative for g, and there's our answer. So both of these rules come straight from rules that we had for limits as well. So now we can think about the derivatives of polynomials. And in fact, we can go a little bit further than that. We can do the derivative of adding any powers of x. They don't have to be necessarily integer powers of x. But let's see how this is done. Find the derivative of 4x to the 7th plus 2/3 x to the 6th minus 2x squared plus 4x minus 3. So in order to do this, I'm going to take the derivative of this function, and I'm going to do this slowly so we can kind of see how this is going to work. But note that when you're doing this on your own, you might be able to do it quicker than I'm doing. So the first thing I'm going to do is I am going to take this derivative and I'm going to break it up over addition and subtraction. So I'm going to write this as the derivative of 4x to the 7th plus the derivative of 2/3 x to the 6th minus the derivative of 2x squared plus the derivative of 4x minus the derivative of 3. Then I'm going to use the constant idea to bring constant out in front and write this as 4 times the derivative of x to the 7th plus 2/3 times the derivative of x to the 6th minus 2 times the derivative of x squared plus 4 times the derivative of x, and then minus the derivative of 3. So what I've boiled this whole problem down to is 1, 2, 3, 4, 5 applications of the power rule, and then I just need to kind of do some algebra past that. So this whole thing is going to be equal to 4 times that answer plus 2/3 times that answer minus 2 times that answer plus 4 times that one, and then minus whatever that's going to be. So the derivative of x to the 7th is 7x to the 6th. We bring the power down out in front, decrease the power by 1. Here's going to be 6x to the 5th. Here's going to be 2x to the 1st. The derivative of x is going to be, we'll do it up here so we can kind of see the details. X to the 1st is going to be 1x to the 0, or just just a 1 itself. We also said that we know the derivative of a line is just the slope of that line, so that's going to be our 1. And then the derivative of a constant is just 0 always. We said that before as well. So putting it all together, we get our answer as 28x to the 6th plus 2/3 times 6 is going to be 4x to the 5th minus 4x plus 4. So note that right now we may do this in lots of different steps. Very soon you're going to be able to do this in one kind of step, and this should be a fairly easy problem to do. In the next video, we'll look at some more practice problems relating to the power rule and these derivatives.